Hello, good morning. Welcome to the NRIS Talks webinar. My name is Dhanya Pushpadas and I work at University of Bergen and I'm also NRIS training coordinator. So those who are wondering what is NRIS, NRIS stands for Norwegian Research Infrastructure Services. That we are a collaboration of the four largest universities in Norway, universities of Bergen, Oslo, Tromsø, and NTNU, and together with Sigma 2. Our core activities are joint operation of our national HPC and storage services, advanced user support and unified user support, shared training and dissemination resources and activities. So as you can see, NRIS Talks is a part of our outreach program where we host webinars on different topics that is relevant for scientific computing. Today, our topic is EESSI. EESSI stands for European Environment for Software Scientific Installation, and it's an innovative service to make optimized scientific software installation available on any machine, anywhere in the world, on real time. But more on that will come later because there are people to talk about it, and I will introduce them within a moment. Before that, I would like to heartily welcome to all of you to this webinar, and I just want to say something about the Q&A. At the end of this webinar, we will have a Q&A, and I would like to say that you use the Q&A tab on the Zoom and ask your questions during the webinar or at the end of the webinar, and we are happy to take it and answer it. And this webinar, as you can see, that is recorded and we will publish it. So to talk about EESSI, we have Richard Topouchain, senior engineer at University of Bergen, a good colleague of me, and he's part of our user support and software team. And he has been actively contributing to the EESSI project. So more on that, he will talk to you. And as a panelist, we have Thomas Röblitz, who has been there in the EESSI project from the beginning, if I'm not wrong, and leading our research data group here at Bergen and part of NRIS as well. So welcome, everyone. And I just want to mention that when you type Q&A, please follow the code of conduct. It is nothing but use respective language. And I wish you a great webinar experience on EESSI, and welcome all of you, and welcome Richard and Thomas. Over to you, Richard, and we are eager to hear more about EESSI. Thank you.
Thank you, Dhanya. Welcome, everyone, and thank you for attending this webinar. In today's session, we will cover first an overview of scientific software installation challenges, then an introduction to EESSI, followed by how to use EESSI on NRIS HPCs, a live demo, and finally, we will wrap up with some related information. Please feel free to post your questions in the chat at any time, and we will address them later. So let's get started. One of the main challenges of building scientific packages is that they have a large set of externally developed dependencies, which in turn bring a large set of related requirements for each unique build. And these may be complex to resolve consistently on different systems. This situation affects both developers and end users of those applications. Traditionally, HPC systems were primarily being used for research in relatively limited subset of scientific domains, such as simulations, physical simulations, molecular modeling, weather predictions, and so forth. While in recent years, the scope of computational science has expanded significantly, with new fields such as machine learning, artificial intelligence, bioinformatics, and others. In several cases, the increased interest in HPCs was a direct result of the huge influx of available data to be processed or utilized, or so-called the big data revolution. Prominent examples of this are deep learning and the next generation sequencing. And to further complicate matters, the landscape of scientific computing has been undergoing significant changes recently in terms of available hardware resources. The vast majority of HPC systems that were installed in the last decade or so have been powered by microprocessors manufactured by Intel or AMD, which support the x86 instruction set architecture, or ISA, to a point where over 90% of those top 500 supercomputers fell in that category. And only a small minority of systems were employing processors supporting different ISAs, like the PowerPC, and the ARM-based processor architectures, which were used in supercomputers such as Fugaku, Jupyter, and Olivia soon. They are quickly becoming the mainstream of scientific computing. This increased variety in the available compute resources has significant impact on the effort that is required to migrate workloads from one system to another. Software that was compiled for an ISA like x86-64 must be recompiled to run on processors that support different ISAs. Last but not least, there is also a growing interest in leveraging the infrastructure that is provided by commercial cloud providers for scientific workloads, either as a replacement for on-premise systems or as an additional resource to the cloud bursting when the on-premises infrastructure is not sufficient to keep up with the demand on compute resources. And finally, the emerging of revolutionary technologies like accelerators and interconnects for general purpose computing has sparked immense interest among researchers across various scientific fields. The broader spectrum of scientific domains seeking to employ computational methods to make sense of the wealth of data, together with the push to make the software that was developed to support scientific research available publicly, and the increased variety in the available compute resources, not only impact the support teams of these high-end systems, who often find themselves struggling to keep up with these support requests, but also the scientific researchers themselves, who frequently lack the necessary expertise to efficiently manage the wealth of tools, libraries, and applications that they require. Sometimes they find themselves limited to the software that they can get working in a short term, or they will be waiting until others can facilitate the installation of the tools that they would like to use. Having this said, we can see that there is a large urge for a better collaboration on a larger scale. Although some software framework like EasyBuild is already there to help in managing scientific software on HPCs, but this is not enough, as there is still too much of software to handle, different operating systems with different problems, duplicate work across different HPCs and clusters, which result in different and diverse software stacks. And there, EASY comes into play. EASY is a project, it's like a collaboration between different HPC sites and industry partners, with a common goal to set up a shared repository of scientific software installations that can be used on a variety of client systems, regardless of the type, flavor, or version of the operating system, which microprocessor they are powered with, and whether it is a full-size HPC, a virtual system in the cloud, or even a personal workstation. The project aims to relieve scientific researchers from the burden of installing the tools, libraries, and applications they require for their work. So, the overall goal is to provide an easy access to a consistent stack of scientific software across different types of client systems, while avoiding compromises that would have a significant effect on the performance and the provided software installations. To achieve this, multiple established existing open source tools like CVMFS, Gentoo, EasyBuild, Lmode, and RSpec have been set together to build a solution consisting of 3 layers. Each layer is responsible for a particular aspect. The first layer is responsible for distributing the software installations. The second is for ensuring compatibility with different types and versions of client operating systems. And the third is providing installations of scientific software which are optimized for different families of microprocessors. The first layer for EASY is the CERN-VMFS. It is a software distribution service developed by CERN, a common tool used in particular by high-energy physics community to make high-energy physics software available to worldwide distributed computing infrastructures, and which is heavily tuned to cater this specific use case of distributing software installations. CERN-VMFS is a network file system, which you can mount on Linux or Mac OS via Fuse, which is file system in user space, or on any Windows subsystem Linux. The installation of the CERN VMFS client required for any user who wants to use EASY is generally very easy, as installation packages are provided for many different platforms. In some ways, CERN VMFS is similar to other network file systems, or AFS. The files and directories in CVMFS are provisioned through a network of servers that can basically be viewed as a web servers, since only outgoing HTTP connection is used. This approach makes easy to be used in environments which are protected by firewall rules or when the use of HTTP proxy servers is required. A CERN VMFS repository contains the actual software installations. A system that mounts a CERN VMFS repository offers access to the software stack provided by the repository as if those installations were available locally on the system. Specific features implemented by CERN VMFS, such as compression, deduplication, aggressive caching, and on-demand downloading of files and file metadata, cater to the specific use of storing and globally distributing software while optimizing the required disk space and network bandwidth. In this slide, we can see the CERN VMFS designed for EASY. We can see that there is a CERN VMFS central server known as Stratum 0. There is also Stratum 1 servers known as the mirror servers, and also a proxy server could be set to further enhance performance. So a user who's using the workstation or an HPC cluster or an instance in the cloud can reach out the EASY software stack. First, the user, when tries to fetch a certain software, if it is not available on the cache and a proxy server is available, the user will reach the proxy server, and the proxy server in turn, if it cannot provide the streamed or desired software, then it will be fetched through Stratum 1 servers. The second layer of EASY is the compatibility layer. In order to support many different client operating systems, EASY provides its own set of operating system libraries and tools, which are leveraged by the provided software stack installation in the software layer. This ensures that the software does not depend in any way on libraries provided by the host operating system on the client, because these operating system dependencies have to be shipped with the stack. The idea was to install a minimal operating system into a non-default location, which is under CVMFS. This is one reason why Gantu prefix was chosen for building the compatibility layer, as it is a Linux distribution built from source that can be installed in any given path, known as the prefix. Furthermore, it supports many different ISAs, including x86-64, ARM, and Power, and can be used both on Linux and Mac OS systems, which is another important reason why Gantu prefix is a very good match for EESSI. The Gantu prefix installations for EESSI are installed into a compat subdirectory of the CERN repository, and the Gantu prefix installation is provided for each ISA. The default Gantu prefix installation contains a quite minimal set of tools and libraries, for example, the glibc or OpenSSL, and some compilers and building tools. All these tools and libraries built from source using Gantu package manager, the portage, which usually provides very up-to-date versions of the packages. This not only ensures that we can provide recent versions of these packages, but also we can quickly update in case of any security vulnerability. On the top of the default Gantu prefix installation, some additional packages needed for the software layer have been added, like communication packages and the environment modules tool lmod. A very important aspect here is that all packages in the compatibility layer provide only generic libraries, as the packages in this layer are not the ones that are critical for the performance of scientific applications, and this allows them to be reused across different CPU microarchitectures. And the third layer of EESSI is the software layer. The software layer of EESSI holds the actual scientific applications, and it is what most users will be interacting with. In practice, the software layer is a subdirectory of EESSI CERN repository with different subtrees for all the different microarchitectures that are natively supported. EasyBuild installation framework is used to build, optimize, and install each scientific application or library for every supported microarchitecture by running on an appropriate build node with the corresponding microarchitectures. EasyBuild also takes care of generating the module files that are used in conjunction with lmod to present the end user with a software module environment, allowing them to load modules that they need into their environment, regardless of the microarchitecture of the end user system. The only difference between these software trees could be related to the application that are not supported by a certain microarchitecture. Selecting the right software tree is taken care of by leveraging the RSpec tool. It allows for detecting a machine's microarchitecture, and in case there is no native support for it within EESSI software stack, it can query for the best matching compatible microarchitecture that is supported by EESSI. So simply by sourcing a shell script or loading a module in case as it is on our NRIS HPCs, this process is fully automated. The path to the right software tree automatically gets reflected into the user's environment. In other words, only one single command is able to make the user access a full stack of scientific software that is optimized for the system they are running on. As we can see in the slide, EESSI supports the x86 ISA and the ARM-based processors. So in the x86, EESSI supports the Intel Haswell and the Skylake. Also in AMD division, there is the Zen 2 Zen 3, and the Zen 4. While on the ARM-based processor, there's the Neoverse N1 and the Neoverse V1. But in all cases, it is either on the x86 or the ARM-based processor, there is the generic, which is basically the non-optimized software. So you are able to get access to the software stack, but it is not optimized for the system you're running on. It is also good to mention that while software testing is important to individual HPC centers that offer software installations to their users, it is exponentially more important in a project like EESSI. Even if only a handful of HPC centers would adopt EESSI to provide software solutions, the impact of a breaking or changing in the software stack could affect a very large number of end users. Following modern software practices, the EESSI project aims to test each individual component, file system, the compatibility, and the software layer, and follow a proper continuous integration and continuous development process, a CI/CD. The goal is to enable running these tests on any of the systems that provide EESSI software stack. Additionally, the test suite aims to be run on any system that mounts EESSI software stack, run within a reasonable time, to test using a single node, or to test using a multi-node for more scaling. The three main use cases for the EESSI test suite is to run a CI/CD pipeline when changes are made in the compatibility layer, run a CI/CD pipeline when additions are made to the software layer, and testing the software stack when the EESSI stack is deployed on a new client machine. In the slide, we can see the different layers of EESSI. So we have the file system layer, which is responsible for the distribution of the software stack, the compatibility layer, which assures leveling, the ground across client OS, the software layer, which offers the optimized applications and dependencies. On the left, we can see the testing tool Reframe, while on the right, we can see different tools used to make up the solution. So EESSI in a nutshell, EESSI is an on-demand streaming of optimized scientific software installations. And we say streaming because the software that you are asking for will be available through the proxy or through the Thread-M1 server, as we have mentioned. EESSI works on any Linux distribution thanks to the compat layer. It offers a uniform software stack across various systems, laptops, HPC, cloud, and again, it is community-oriented, so challenges are tackled together rather than each HPC support team tackling its own. On this slide, we can see a proof of concept performance evaluation. This has been done on a supercomputer in Jülich. We can see that although EESSI provides different stacks as the generic or the most optimized Zen 2, we can see that the optimized stack performs much better than the generic one in EESSI. And it also performs as good as the scientific software stack offered by the supercomputer or the software that is available on the supercomputer itself. The EESSI user experience is really easy. So as we mentioned, first, we have to load the module. It checks the local client cache if the requested software is there. If it is, it will be directly delivered to the user. If it's not, it will go to the mirror server and then deliver it to the local client cache and then to the user. And the central server, which is Stratum 0, Only the administrator has access to change and modify the data there. And the mirror server assures always to be kept up to date with the central server to deliver the latest software that is continuously being set or built on the central server. So EESSI provides an on-demand streaming of scientific software, just like music or any TV series. Having mentioned earlier, EESSI is a pivotal component in the multi-xCare project. It is a 4-year project. It's a collaboration between EESSI and SECAM, a total of 16 partners, academic and industry. EESSI focuses on the technical aspect of providing a shared stack of scientific software, and the scientific part is targeted toward simulations with 3 use cases: the helicopter design and the certification for civil transport, the battery applications to support the sustainable energy transition, the ultrasound for non-invasive diagnostics and biomedical applications. Multi-xScale is co-funded by the European Union and by the Euro-HPC joint undertaking. And thanks to this funding, we are able to better support users for EESSI. And it is also good to mention great thanks to the Amazon Web Services and Microsoft Azure for generously supporting and sponsoring the EESSI project with cloud credits and feedback and the guidance. And because of those credits, we are able to build the software supporting different microarchitectures. There is also the support portal for EESSI, which is on GitLab, where a user can report issues or request software. And it is also good to mention that there is also a best practice for CERN VMFS in HPCs. It's an online tutorial. You can find it on the multi-xScale website and also on YouTube. Next, we will do a live demo on the national HPC systems for NRIS. And it will be held in 2 parts. First, we will be only loading EESSI module on the login nodes and show how the same software with the same version is available on different machines, Saga, From, and Betsy. We will not run it because we are not supposed to run software on login nodes. While in the second part, we will cover and run a test case of GROMACS on From. We will further explain while loading this module. I will stop sharing and my colleague Thomas will share his screen while I can further explain. I have mentioned we will be loading the EESSI module on the 3 different HPC systems, Saga, From, and Betsy. It is pretty simple. Just by doing a module load, EESSI 2023.06, we will see that the module will be loaded. This is on, we executed the module load on Betsy, now doing it on From. And we will also do it on Saga. After loading this module, we will search for a software randomly. Let's search for TensorFlow. And okay, now we can see that EESSI has been loaded. EESSI module is loaded. So we will do a module avail TensorFlow. Here we can see that TensorFlow version 2.13.0 using FOSS Toolchain 2023A is available through EESSI. The main difference here is that TensorFlow that is provided through EESSI on Betsy is optimized using the Zen 2 microarchitecture, as you can see. While doing it on From and Saga, we notice that we will go to From now. Yeah, now that the module is loaded, we will search for TensorFlow on From. We can see that the same version of TensorFlow 12.3.0 using toolchain FOSS 2023A is available. But here we can see that the best match of the CPU microarchitecture on From is Haswell. And if we can go to Saga, again, we will search for TensorFlow. We see that exactly the same version with exactly the same toolchain 2023A, but again, here it is optimized using Skylake microprocessor architecture. So the same software stack is available on different machines with different CPU architectures. Now, to further demonstrate, we will run the same example that is available on NRIS support website, which is used for GROMACS. So we will run a test using GROMACS first on using the local system GROMACS, and then we will run it using EESSI. So can we run the SPAT job for GROMACS, the local GROMACS? Earlier we had some issues with.
Yeah, I guess I'm not a member of that project, so I could just.
Yeah, and the reservation should be changed to CVMFS tests. CVMFS tests.
Like this?
An S. It still needs an S after test.
Tests. Like this?
Yeah. This should work now.
Yeah, like this. Okay.
Yep. Can we try running it?
Local, like this.
Yep.
Okay.
Okay. Perfect. And we can also run at the same time the one with EESSI, because afterwards we will compare them together. So we were doing a live demo on Saga from and Betsy for loading the module. And before the fire alarm went on, we were doing running a batch job for GROMACS. So now I guess the job has finished now. We will show and compare running the GROMACS software that is available on the system with the GROMACS, which is delivered through EESSI. So if we can do a Vim diff showing both on the same screen. As we can see, the tab on the left shows that the software or GROMACS used is from the cluster, that is the GROMACS on the system itself. And on the right, we can see that it is the one chosen from EESSI, that is because it's using the CVMFS. And as we mentioned earlier, it is using the best optimized, so it's not using the generic. As we can see, the numbers go down the screen, please. And the numbers are pretty close. The small difference could be because the version of GROMACS on the system is different than the GROMACS version that we are using on EESSI. But all the other options, it's a load balancing or the performance, we can see that they are pretty close. And we saw that simply by loading EESSI module, we were able to get access to a full software stack. So a single difference in the batch job between local software and EESSI is just loading EESSI module. I will take back the screen and proceed and wrap up with what we had. So to wrap up, I will, and as a related information, as we have set in the agenda, I will give a highlight of how additional software is added to EESSI. So first, when a contributor wants to add software to EESSI, first he should make, or she should make, the contributor should make a PR on EESSI software layer. Then there is a bot which takes care of building this software on specific nodes which have different microarchitectures to build specific software for those architectures. As we said earlier, there is Haswell, Skylake, Zen 2, Zen 3, Zen 4, Neoverse N1, Neoverse V1, and generic in both x86 and ARM-based. So the bot takes care of automatically initiating jobs on those different nodes. And after the software is built, there is a testing that is done. Then the software is put in a tarball, transferred to an S3 bucket, where jobs pick up those software and push them to the Stratum 0 server. As we already mentioned, only administrators have access to the Stratum 0 server. A PR is opened through GitHub, and then there are some colleagues who review those pull requests, and then this package is automatically deployed in EESSI repository, and it can be accessed through any system. Thank you all for joining us today. I hope the session met your expectations beside the fire alarm. Your feedback is very valuable and it helps us to choose the topic for our next EESSI session. So please make sure to complete the survey. We appreciate your collaboration and attendance, and we look forward for seeing you again.
Yeah, before
Now
that,
I will hand it over for you, Dhanya,
thank
so
you.
that we can go on with the Q&A.
Yes, thank you so much for the great session, Richard. And I apologize for the fire alarm and this little disruption during the event. We didn't anticipate, or no one anticipated. But we will record these sessions and avoid this little disruption. And I will send you the link when this recording is available for you. As Richard mentioned, we will go through the Q&A. If you are around, any more questions, you please go ahead and ask.
So we were trying to go over the Q&A.
Yes.
I typed something, but somehow I lost what I typed. So there's the question about some problems with EESSI build. Maybe I can read the question if people don't read it. Two examples of problem. One, the available EESSI build recipe ignores the possibility of integrating a master software package with other packages. So the integrated software installation cannot be created with EasyBuild. So I would assume that means that something like some software that is already available on the system cannot be used with EasyBuild. To the best of my knowledge, EasyBuild can use such software, but it depends on the recipe. So if the recipe is not prepared for that, then of course it doesn't use it. But I know that, for example, on Lumi, it's very important to use the existing packages on the system because the vendor provides a highly optimized communication libraries, for example. Yeah, and it was very important to use them. And EasyBuild is used on Lumi for building software. And then the second part is, okay.
Yeah, I can add one more thing here that in today's session, we were focusing on how to use the already existing software. On later upcoming sessions, we might focus on how to build on top of Easy. So I guess that could cover what Marco is asking for.
Yeah. So the other question, EasyBuild build a corrupted package that does not really provide full functionality. That could happen. Yeah. So, but that I would think also is maybe a problem of the recipe or a problem of the setup, and then one would have to look into the error messages and find a solution for that. What we do when we build for Easy, we run, so every software, not every, but most software packages, they come with some unit integration tests, and those tests are run. And we also check if there was any error during the build, and we only add software to the software stack when we have seen no errors. Yeah. There was a follow-up question. What to do if the list of available software does not contain the ones that one needs? So there we have Easy has a contribution policy. So basically what we say is that we want to use the most recent EasyBuild version. We want to use recent tool chains. And of course we cannot distribute commercial software and things like that. Yeah, but if those conditions are met, then software can be easily added. Richard has shown this procedure we use, and it's very easy to add software to Easy. Yeah, so one necessity is also one necessity is also that there's a recipe for this. Yeah, and one could try to make a recipe by yourself, yeah. But if you don't have that, then Richard also mentioned this support portal, support email address, but one can also help with that. Yeah.
There is another question. Are you taking
there's another
it?
question? Yeah, I can just read it. Our team is working
again, but to add something, and I've already mentioned, so maybe upcoming sessions will focus more on how to add software to Easy. So there are different scenarios, but we make sure we will cover those on upcoming sessions.
Yeah, for this, I think, as Richard already mentioned, it would be good to understand a bit from, in addition to what we presented today, what is important for you. Yeah, it could be using Easy on your own system, and then we could explain this in more detail, how to install CernWFS clients, configure it, and use it, and maybe troubleshoot some issues you may run into. Or you could, as someone asked us, so how to add software that is not available. Yeah. And maybe there are other topics. Yeah. And there's another question. Our team is working now in accelerated code for GPUs. Yes. So at the moment, so the question is basically, will there be also software that makes use of GPUs? And we are working on this. We have a little bit software for GPUs already, but not so much at the moment. There's one tricky issue supporting GPUs is that you need some CUDA and some other libraries from NVIDIA. And unfortunately, we cannot distribute all software or all parts of that of these toolkits. Yeah, but we have a solution for that, so don't worry. Yeah, but that's just something to keep in mind. But if that is of interest to you specifically, we can also look into this. Yeah, to make a course or tutorial for that.
Yeah.
So as my colleague Thomas mentioned, the design for GPU support in EESSI is already there. And if you check the EESSI software stack, there is also CUDA where you can do some tests. But again, there is this licensing issue for distributing the software we have to be careful for, but I guess it's coming. So an effort is being set now and put for making this happen. Yep, Dhanya?
Thank you. Thank you for answering this accelerator question as well, Thomas and Richard. But I have one general question about the support on EESSI. So if an NRIS user wants some support on EESSI and the user outside NRIS border wants to get some support from EESSI, what would be the suggested way of go? Where should they ask support?
So for EESSI on NRIS HPCs, the user can reach out through the support page or can open an issue on GitLab. Just make sure to mention EESSI in the subject and we will take it from there.
So if a user uses, for example, Saga from Betsy, then of course they can ask the standard ways to get support on these systems. Yeah, and I think we are also working on getting EESSI on NERD. Yeah, and yeah.
Just a comment. NERD is our storage cluster at NRIS.
Yes.
Yep.
Yeah, and but it could be that maybe you are interested in using EESSI not on these systems but on your own machine or in the cloud somewhere. Yeah, that could be that maybe the question fits better to the sort of central EESSI support channel, let's say like this. Yeah, and then you could either reach us via the support@eeessi.io email address. Or if you have an account on gitlab.com, you can also, I think you can also file a case there directly for the EESSI project. Or maybe that was in the slides, I didn't see. Maybe there's links to both the documentation we have about EESSI and how it's implemented on our own systems, but also to the EESSI project as a whole. Yeah, and there's a lot of documentation already available, and there should also be links to how to get support.
Yeah,
we mentioned eeessi.io in the slides, and there I guess if anyone outside NRIS is interested to run EESSI on their systems, they can find some very useful information. Yep.
Yeah, so these slides will be shared after the event. The final email, I will send it out. You will have the recordings and slides. So if you don't find it, if it's difficult to find it now, this material will be available for you. I think we are approaching our time. 1 minute. I would like to thank Richard for this good presentation, and Thomas, thank you so much for joining the panelist and answering all the questions. And also all the participants who were interested to join this webinar. And I hope you had something to take away. And as Richard and Thomas mentioned, support will be available for this for the use of EESSI. So please go through this documentation and please feel free to reach out this EESSI consortium or NRIS support if you have any questions. And thank you for your participation and thank you for presenting and joining the discussion, Thomas and Richard. I will conclude this and I just want to remind you, please give us feedback. You will get a feedback questionnaire when I close this, and please give us, and it's very important. And also add if there is something more you want to hear about EESSI. There is one question regarding that. That would be great for us to arrange any kind of training or webinar related to EESSI and also all other generic questions. And your feedback is very valuable. And we really appreciate your feedback. Thank you again and hope to see you in another training events at NRIS or our collaborative events. Great. Bye.